Hello and welcome. As promised, this is part 2 where we look at the famous Basel problem. Don't worry if you've never heard of it, I'm going to tell you what it is and a little history on the Basel problem. So first of all, the problem is actually quite simple. It is asking what is the answer to 1 over 1 square plus 1 over 2 square plus 1 over 3 square, so on and so forth. However, the answer is very difficult to get. First of all, because this is an infinite sum. You keep adding on forever. Okay, so here is my poor attempt at trying to solve this. I only worked out the first 4 terms and I used a calculator. Okay, I'm going to talk about quite a few famous mathematicians and all of them did not have a calculator with them when they worked out their answers. Okay, so I worked it out to be about 1.3-ish. Yeah, that is my answer to the Basel problem. Now, let's look at some of the famous mathematicians who tried their hand at this famous problem. So the first one is John Wallace. You might know him as the person who invented the number line. Now we use the number line for many things like solving quadratic inequalities, linear inequalities, or just teaching children how to count from 1, 2, 3. Use the number line. He was also the person who invented the infinity symbol. Okay, so John Wallace managed to work it out to 3 decimal places. Okay, he claims to know it to 3 decimal places. So he probably worked out more than just the first 4 terms, right? And let's move on to the next person, the next victim, and that is Jacob Bernoulli. Now, do not confuse Jacob Bernoulli for Daniel Bernoulli, because I know you're thinking about the Bernoulli effect, right? The phenomenon that allows airplane wings to gain lift when air passes through them. That is Daniel Bernoulli. Now, the Bernoullis are a Swiss family that's well known for producing a lot of academics. Okay, so there are many smart Bernoullis throughout history. So Jacob Bernoulli says that is less than 2. He is well known for working out Bernoulli numbers, coming up with Bernoulli numbers. So if you don't know what Bernoulli numbers are, let me just ask you a simple question. Have you ever come across the Maclaurin's expansion for tangent x? Well, you haven't, and that's because the coefficients of tangent x, right, in the expansion, Maclaurin's expansion, is truly very complicated and very complex. But you can use a Bernoulli number to represent it. Okay, and this Bernoulli number is not only used in Maclaurin's expansion, it's also used in other areas of mathematics. Most notably, it is used in certain values of the Riemann zeta function. Now, if you ask any mathematician, they will know that the holy grail of mathematics is the Riemann hypothesis. Okay, this is a problem that if you solve, you get $1 million cold hard cash. So if you're gunning for $1 million, you can try a hand at the Riemann hypothesis. Now next, we have Jacob's brother, Johann. Johann Bernoulli says that it's about 1.6. Okay, he is well known to be the tutor of the person who is going to eventually solve this, and also the tutor of L'Hopital. So who is L'Hopital? If you're trying to work out limits of a certain expression, you tried simple substitution, you tried partial fractions, you tried substitution, you tried a lot of things, but it just doesn't work. Well, you might want to try L'Hopital's rule, which is to differentiate the numerator and the denominator. Okay, and then do it again, you should be able to get the limits this time. Okay, so interesting fact is that actually Johann Bernoulli is the rightful inventor of the L'Hopital rule. It's actually quite an interesting story. You can read it up just by Googling it. You're going to have a good time reading up, I promise you. Next, we have Christian Goldbach. He narrowed it down even further to between 1.64 and 1.6 repeating. Okay, so Goldbach is famous for his conjecture. He has this conjecture, which means it's something that we have not proven to be true. We have not proven it to be false either, right? We just don't know whether it's true or not. He says that every even integer greater than 2 can be expressed as a sum of 2 prime numbers. Okay, I think we have worked up to 400 million or 400 billion by now, but we still don't know whether it's true or not. Okay, so that is Goldbach for you. Other notable mentions will be Leibniz, co-founder of calculus, and De Moivre, right? If you do complex numbers, you'll know De Moivre's theorem. Okay, so who is this rock star who has solved this Basel problem? His name is Leonard Euler. Okay, to say he is a genius is underselling it. Okay, so here's an excerpt from Wikipedia, right? And I just want to show you this part in green. It says that Euler's work has touched upon so many fields in mathematics that if you were to look up a reference, right, the earliest reference to anything, you will probably find his name. Okay, so imagine a scenario when, oh, I just made a mathematical discovery that any map that you draw on a piece of paper can be colored with using only 4 colors. Well, guess what? Euler was the first one to discover that fact. Or if you find out something like, wow, do you know that mathematics can be extended to shapes like donuts and Mobius strips and you can use them to solve complex equations? Well, Euler actually did that as well, right? In fact, in order to avoid having everything called Euler's theorem, Euler's theorem, Euler's theorem, Euler's theorem, we had to name all these things after the second person who discovered it. Right? That is pretty savage if you ask me, right? This guy is truly the rock star of mathematics, Leonard Euler. Okay? So his solution to the Basel problem is, it's not 1.3, it's not 1.6, 1.64, 1.66, it is pi square over 6. And you'll be like, what? It's not even a number, it's an irrational number, pi square over 6, which is 1.644 something, 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 something. Okay? And you're wondering, how did he do that? Well, let me tell you, if you have watched part 1, have the exact knowledge that you need to work out pi square over 6. Okay? What you need is to know is the Maclaurin series for sine of x, and also the same sine of x, but written as an infinite product of terms. Okay, and I'm going to show you very quickly how to do it. First of all, what I'm going to do is I'm going to divide both of them by x. Take sine of x and divide by x, divide by x. Okay, so this one becomes 1, this becomes an x squared, this becomes an x to the power of 4. Now for the infinite product, we just need to drop this term. This one just disappears. Okay, so that's relatively easy. So let's look at that. Okay, so now I have sine of x over x, and I have my Maclaurin series this way, and my infinite product this way. Next, I'm going to compare the coefficients of the x squared term. Compare this and the coefficient of the x squared term, or this infinite product. Okay, so on the left hand side, I have the x squared term using Maclaurin series, and the right hand side, I'm going to write down the x squared term from the infinite product. So now we need to think about how to expand an infinite number of brackets, right? How do we expand it out? So what I'm going to do is I'm going to introduce this idea that inside every bracket, I have 2 terms. It's like a binomial. Okay, so I have a left term, I have a right term. Left and a right, left and a right. Now, I can tell you for sure that my first term, if I expand out infinite brackets, it's going to be 1. Why is it 1? Because I'm taking the left term from the first bracket, multiplying by the left term on the second bracket, left, 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 all the way left. It's all lefts, right? That will give me 1. And all the ones are positive. Okay? Then how do I get my next term? Well, instead of doing all lefts, I'm going to start with a right. I'm going to take this right and multiply by left, 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 left. And then my next term, which is the x squared term, will be negative x squared over pi squared. That would be my first term, my x squared term. Now my second term would be left, right, left, 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 left. Okay, so I take the first left, which is a 1 positive, multiply by a negative x squared over 2 pi squared, then multiply by 1s all the way. So my second term, my second x squared term, is going to look like this, over 2 pi all squared. And you can see how this pattern continues. I'm going to get x squared over 3 pi all squared, so on and so forth. Now, if I only want to look at the coefficient, meaning I don't want to look at x squared, okay, I can sort of say that, oh, you know what? That means negative 1 over 3 factorial, which is negative 1 over 6, is equals to negative 1 over pi square, negative 1 over 2 square pi square, negative 1 over 3 square times pi square, and so on and so forth. Next, I'm going to multiply by pi square on both sides. And what you have is, since I multiply by negative, it becomes a positive pi square over 6. And on the right hand side, you're going to get 1 over 1 square, plus 1 over 2 square, plus 1 over 3 square, plus so on and so forth. And there you have it. You have just solved the Basel problem. Pi square over 6, right? In what? 4 or 5 steps, right? So this is really a snapshot of the genius of Euler. When I first saw this, I had goosebumps, right? Even now, I'm still getting a bit of goosebumps just looking at how he managed to do this, right? So I hope this has been interesting or mind-blowing for you, and I hope to see you next time, hopefully in another mind-blowing and interesting video. Until then, catch you on the flip-flop.